Oh, I just started the recording. Yeah.
I've totally, I've gotten over my self-consciousness during
Okay.
the Zoom era about like what I look like and sound like in recordings. So
Yeah, yeah, I would say me too, but I just choose not to listen to recordings. So if I don't listen to them, I can't be self-conscious about it.
Sorry, I plugged in my webcam and my computer crashed. It's my bad, guys.
Your computer couldn't handle it.
How are you, Dr. Stone?
pretty good, pretty good.
Good.
It's great weather this week, which sort of eased the trauma of the early sunset.
Yeah, absolutely.
I went out with a winter jacket in like the 70-degree weather, like unknowing that it was like actually 70 degrees. Someone was like, dude, it's like hot out there, right? And I'm like, oh. So I was like sweating.
It's very strange with how early it gets dark now. I was coming back in the train and it was pretty much nighttime, and it was a very surreal experience for me. Just to be I don't know, I felt like I was working like a 9 to 5 job or something. It's very, very funny. But yeah. How many people do we have? 10? Bit less than expected, but it is exam season, so understandable. What time is it? 8. Do you mind if we wait around 3 or 4 minutes for people to trickle in, Dr. Stone?
Oh no, that's fine.
Cool.
Yeah. I don't have any meetings after this.
Nice. Okay. Well, less for the meetings and more about you wanting to get done with your day early.
I'm just temp.
All right. I think we can get going. Um, all right, I'll give you a brief introduction, Dr. Stone. So, hello everyone. Thank you for coming tonight. Today we're going to be having Dr. Stone speaking with us today. Dr. Stone is a professor here at Rutgers. He teaches some CS courses, and he studies mainly. Correct me if I'm wrong. I think it's natural language generation and cement like computers understanding like natural language semantics and all that. Correct?
Yeah, I'll be talking about that today, in fact. So.
Awesome. Okay. So yeah. Without further ado, Dr. Stone, take it away. Thank you very much.
Thanks. So I wanted to preface this discussion with a bit of context. So one thing is that if you are interested in like the connections between computer science and cognitive science, and more generally in intelligence and the way in which the technology that gets deployed using sort of ideas from AI, sort of impacts society and relates to human intelligence, there's a really outstanding set of opportunities and discussions and debates and kind of research opportunities to be part of at Rutgers. And so I put a couple links to that in the chat. The Critical AI group, the Cognitive Science Center sponsors it. And they're looking this semester at the kind of social and conceptual and technical and legal implications of big data. And the next talk in the series is tomorrow evening with a bunch of law professors debating data-centric AI. These kinds of things are eminently accessible to undergraduates because it's really meant for a general audience. And it's a really high, a lot of the speakers are very well known and are at the kind of cutting edge of the field. And there's recordings available on the site for the events this semester, as well as the events that they did last winter, which were amazing. So I happen to have given a short technical introduction to some of the computer science ideas in natural language processing that are really energizing the field. And for people that have more CS interests, this recording might be a better presentation, sort of more suited to your interests than the thing that I'm going to talk about tonight. Because as I make clear in that other presentation, a lot of the ideas that animate AI actually have very little to do with cognitive science. And that's especially true when it comes to language, because the kind of cognitive science of language is obsessively and correctly focused on the innate knowledge, drives, and learning abilities that enable human infants to accumulate and invent vast amounts of knowledge about their native language in astonishingly short amount of time with no explicit instruction whatsoever. So I'm going to really bracket computational techniques in my talk tonight. And what I'd like to do instead is to kind of advertise the appeal of cognitive science as an approach to natural language understanding. And what I like about cognitive science, as opposed to this kind of brute force AI, is that it substantiates intuitions about how language works that are sort of elegant and natural, and in many ways, like kind of really deep-seated assumptions about how people understand language and communication in their own everyday lives. And the kind of idea that I want to really explain is that, like, when you give somebody an instruction in English, you're actually just telling them what you want them to do. It turns out that I believe that that's true. And I believe that, you know, sort of when we have in 10 years or 50 years or 500 years, you know, assistive robots on the model of C3PO, you know, attending to our every need, we will speak to them that way, that we'll tell them what we want them to do and they'll do it. But it turns out that it's understanding what that means in a kind of humanly meaningful way is a really deep tour of linguistics, of psychology, of the kind of common sense world, and the principles of collaboration and social cognition that underlie the kind of social interactions that people have with one another. And so what I wanted to do was just to give you a tour of that as a kind of inspiration, hopefully, for in your own studies, like piecing together ideas from different fields to get like kind of simple, elegant, kind of common sense explanations for these everyday abilities that we people take for granted, but that we are incapable of reproducing in our technological artifacts. You know, so I was actually a cognitive science undergraduate major. I did my Bachelor of Science in Cognitive Science, graduated from Brown in 1992. I chose to do a cognitive science major because it let me take the linguistics courses and the computer science courses I wanted to take, and freed me from taking the linguistics and computer science courses I didn't want to take. So I skipped phonology and I skipped operating systems, but I got to learn the lambda calculus in 3 courses as a sophomore. So that was heaven. And I did a PhD in computer science at the University of Pennsylvania. My PhD supervisor was Mark Steedman, who's now at the University of Edinburgh. And before going there, I asked him, you know, should I apply to the linguistics department or the computer science department? And he said, you know, apply to the computer science department, you can get better jobs. That is in fact still true. And for anyone that's thinking of graduate work, you know, obviously by far the most important thing is to have a supportive mentor, like Mark was for me. You know, when you look at, there probably, you know, there may very well be more computational linguistics professors right now than there are linguistics professors. And there certainly are more computational linguists than there are linguists. So if you're, you know, if you know, sort of computer science needs cognitive scientists, where we've maxed out on the brute force deep learning people. So there is room for a research career that really emphasizes these kinds of human science ideas. And I think it's really important for the success of the kind of technology that we want to build for academia to flourish, and for these really beautiful ideas to get their good hearing, that people pursue them. And anyone that wants to reach out to me for more opportunities, don't hesitate to write an email. And then when I don't answer, don't hesitate to write a week saying, "Are you okay?" And just bear with me. I am the chair of the computer science department, which means that a lot of what I do during the day is, as we like to say, on fire. So let's take we've got C3PO. Like, what are the kinds of things that we're going to ask C3PO to do? Like, maybe, sort of, it's far in the future. It's not so easy to navigate, whatever our East Village walk up or whatever. And, we've come home with shopping, and we're going to need C3PO to carry the bags upstairs to continue our independent, sort of independence, let's say. Right. So what is C3PO supposed to do? And I don't want to make that like kind of problematic. We'll see that there are lots of what Ernie Davis calls computer ambiguities inherent in these. But what I really want to do is sort of bring out along the way how linguistic, psychological, and social knowledge are sort of effortlessly intertwined in the way that we cross these instructions and the way that we follow them, the way that we know what they mean. I have the chat window open, by the way. I have a little window on my screen that shows a few people. So you can stop me at any point. It's very easy as a professor to just lecture. And I don't know if that's really what you signed up for. So I'll try to add some opportunities to appreciate the kind of humor and the kind of understanding we have of sort of how things could go wrong in instructions like these. So I want to start with just what what a linguist would say about what the verb carry means. And I don't know how sort of raise your hand if you've taken a semantics course in linguistics or something like that. Semantics in linguistics is kind of famous for being very abstract about the meaning of individual words. You'll just say that, like, carrying is a kind of event or a kind of activity, and that's in some sense all that the grammar really knows about it. And that's a reflection of the fact that verbs in languages like English are open class items, meaning that essentially for any activity that you can imagine, for any kind of change that happens in the world, your language, your native language, will have a way of interfacing that description of the world into the grammar of the language. So the grammar really doesn't see what carrying is. It just sees a few features of the event that explain sort of what kind of grammar that word is going to have. So in particular, like to say that carry characterizes an activity means that it's an active ongoing effort by an agent directed at a theme. So like you always have to carry something. You can't just carry, whereas, by default, there's a kind of indefinite duration associated with it. Like, if you're carrying a backpack, like you can put that backpack on in the morning, you can board the bus, you can, stand in line, you can, walk to your dorm room, all those things, you're still carrying that backpack during that time. So there's no inherent endpoint or goal to carrying something. It's just something you can keep doing. But one of the things that the grammar notices about carrying is that when you carry something and you move, the thing that you're carrying also moves. And so there's a special grammar in English for motion events, which describe how the theme moves in English. And carrying, the grammar marks it as participating in these kinds of constructions. So for those of you that are interested in the linguistics of it, this notion of an activity, of a ongoing process that is caused by an agent, has an indefinite duration and no inherent endpoint, is a notion that goes back to philosopher and linguist Henk Fekkeil in the early 1970s. And it was formalized in linguistic semantics in influential work by David Dowdy, who for a long time was a professor at the Ohio State University. The idea that the grammar would sort of pick up particular features of verb meaning and use that in a kind of formal description of the kinds of sentences that the verb could use is an idea that was really promoted by the Stanford linguist, Beth Levin, who wrote an amazing book called English Verb Classes and Alternations, which, if you're a linguist, is a treasure trove of those kind of mysterious differences between different linguistic expressions that sort of tickle you with unexpected ungrammaticality and point to the kind of deep principles and universals that go into our understanding of language. So how exactly does this go? How do you use that information that like carry characterizes an activity, right? Like, well, sort of it makes kind of common sense, but then what happens is that is the ingredient then that sort of triggers a bunch of processes, a bunch of rules that sort of indicate how the event described by a sentence in English is related to the different kinds of information about that event that you express partly through the verb, but partly through the other arguments of the verb that go into the instruction. And in some ways, my advisor, Mark Steedman's most famous contribution to linguistics was this contribution of kind of recognizing that the meaning of events is constrained in terms of characterizing a preparatory process, then a kind of culmination point where a change of state happens, with a result change happening afterwards. And this is an idea that actually was also developed influentially by a bunch of linguists that had big parts of their careers at Rutgers, Jane Grimshaw and Maria Bittner. So what happens is that you have this kind of framework that any event involves some kind of continuous activity that suddenly leads to that tipping point beyond which some kind of result happens. And then the grammar, based on the kind of preparatory process and the particularly like motion, explains how the verb meaning or the object denotation or a path expression maps out into a particular kind of motion event. So although carrying is an ongoing activity of indefinite duration, in English, any expression that has a verb, an object, and then a path expression can be interpreted as an event of caused motion where the object traverses the path during the event. And that's what happens in carry the bags upstairs. So we have this activity denoted by the verb, but we have this sentence frame that says this is an event where the object moves along a path. And together what you get is an event whose mode is carrying, during which this object winds up at the top of the path. And so while carrying your backpack around campus is an open-ended activity, carrying the bags upstairs represents a delimited event with a clear result. There's the idea that things have like clear delimit, the sort of properties of events are related to the properties of the argument is a really, again, a very deep idea. That in linguistics, if I were to put like one name on it, it's Manfred Krifka, who's at Berlin, I believe now. So the idea is that like when you, like if you carry your bag around campus is an indefinite path. So carrying the bag around campus is also an indefinite event. Whereas the path, let's say from cognitive science to the student center bus stop is a delimited path with clear endpoints. And so carrying your backpack from the cognitive science center to the student center bus stop is also a delimited event. And this is a really kind of rich and interesting domain because also there's an open-endedness in the arguments that you can describe. So while carrying your backpack from CogSci to the student center is a delimited event. Carrying books from the CogSci center to the student center, it sort of depends on how you conceptualize things. If it's many loads of books, it's something that can be repeated indefinitely. And so there's both the path that you take and the kind of nature of the objects that you're participating in the event influence this way that events get measured out. Which is just to say that like when we say, oh, carry these bags upstairs, if you think that you're going to be able to carry both of those bags, like it's 2 bags and you're going to carry one in each hand, or, it's an octopus robot and you're going to have 8 bags, 1 in each hand. You can do it in one trip and then it's a delimited event. But if you think of it as an open-ended set of bags, and you imagine the robot taking multiple trips, then that's an open-ended description. In which case, you might very well need to tell the robot when to stop. And if you're interested in the problem of telling a robot when to stop, a Stanford researcher called Colleen Krangle has written the definitive paper on telling a robot when to stop. Sort of spoiler alert, the robot can't, there's no way for a robot to stop doing everything that it's doing. And even if there was, you wouldn't want it to do that. Okay. It's important, sort of one of the added wrinkles to this is that there are particular stages in this event that the grammar can sort of focus your attention on. So when you say I carried the bags upstairs, this perfective aspect, it's called, just says that the event took place. But with the imperfect aspect, I was carrying the bags upstairs. Perhaps you got interrupted and the bags never actually made it upstairs. On the other hand, if you say I have carried the bags upstairs, I've carried the bags upstairs, then you'd normally infer that the result state holds, the bags are still upstairs. And so this difference between this sort of focus on different aspects of an event, as the event is described holistically, but then grammatical aspects kind of calls attention to one aspect, one part of it or another. And it's an important kind of wrinkle to the grammar of events that any kind of robot instruction follower needs to take into account.
Quick question, Dr. Stone.
Yeah.
So this is something that's unique to this idea of like having a very open-ended versus like a delimited definition for a particular action. Is that something that's purely dictated by the verb? So I know you said that it can also be dictated by the object, right? Saying bags versus one bag, meaning multiple trips versus one trip, right? Are there any other? I was gonna ask. Is it just? How do I? Is it just English, or is it? Do you know if it's just English that does this, or are like all natural languages, or like spoken languages, like or many spoken languages operate in this way where they have this kind of open-endedness to their events?
So what I would say is that my guess is that every language has constructions, some kind of grammatical resources that can signal both indefinite events of an indefinite extent or bounded events. But many languages will use kind of very different for this. And so one of the things that you see a lot across languages is a process called incorporation, which is the specialty of Rutgers linguist Mark Baker, where if you say I carried the bags, that would sort of inherently be a delimited event. And if you wanted to describe that in terms of an indefinite activity, you'd have to say I bag carried with a kind of compound. It makes more sense if you think about like leaf blower is something that kind of works this way in English. So if you say I blew the leaves, off the driveway, that's a delimited event. But if you say I leaf blew the driveway, that's not in any way, you don't necessarily have to stop leaf blowing the driveway when the leaves are off the driveway. You can just keep going indefinitely with your leaf blower. And that's sort of how Mohawk works. It's to some extent how Turkish works. And it's markedly different from how English works. So the distinction, and in terms of this like grammatical aspect, that's very particular to English, and sort of even characterizing the very different sort of spectral properties of other languages, like particularly the Slavic languages, is very challenging and theoretically rich and interesting. Yeah, so like everything else, there's a kind of important commonalities across languages, but lots of meaningful differences. And I think is the way to think about it.
Thank you.
Thanks for that question. I mean, it's I don't, sort of, there's always a challenge in an audience like this that on the one hand, you're giving examples in a language that you hope your audience understands, because the kind of rich reasoning and the kind of subtleties of the grammar you want to resonate. But of course, a lot of the interest in linguistics and in the science of language generally is in the sort of constrained patterns of variation that you find. Thanks. Okay, so that's kind of how you get a kind of linguistic meaning out of this. And you see that the grammar is doing a lot for you here and sort of, sort of assembling these kind of concepts into a much more precise description of the kind of change in the world that the instruction, is calling for. But like, what is carrying? Like, we haven't said anything about that. And so this is where you kind of have to veer into psychology and out of linguistics. And the message, I would say, about what carrying is that it's engaging with this rich kind of common sense and perceptual understanding that we have of physical dynamics in the world. So what it means to carry something is to support it in a way that leaves it free of other contacts, other kinds of support. So it moves with what's carrying it. And it's different from merely touching or grasping or holding, because it has that understanding of freedom, right? And what's amazing about this is simultaneously like how practically useful this concept is, but also in a sense that you might not appreciate at first, how abstract it is, in that carrying isn't something that you recognize based on the pose of the carrier or the trajectory of the object. It's really about the kind of physical connection that's making it possible. And if the audience will forgive this slightly bro example that I found on the internet, it's kind of really vivid illustration of how independent carrying is of the what the agent is doing, what the thing being carried is doing. It's purely an expression of this kind of abstract physical relationship between the thing being carried and the carrier, that the carrier supporting it in a way that makes it free to move. Right? And so you might be holding it in your hands, you might be holding it in your arms over your back, you might be supporting it on your back, you might even be having it overhead or whatever else. It's all carrying, right? There's some amazing work in cognitive science really substantiating the idea that the visual system and the kind of action representation system could be capable of sort of directly perceiving and reasoning about these kinds of abstract physical relationships. And sort of the pioneering work along this lines was work by Richard Mann, Jeff Siskind, and Alan Jepson, which sort of segmented a video in terms of the kind of events of causal physical changes in terms of how objects were dynamically interacting with each other. And in recent research, particularly I would say in Josh Tannenbaum's lab at MIT, people have been able to do much more sophisticated things along these lines. It's, I think it's a funny thing because it's so intuitive on the one hand and so counterintuitive on the other hand, in that, like, of course, like, it's not interesting what pose you're carrying something in. What's interesting is that you're doing it to get something from here to there. And so that requires the physics to be right. But just approaching problems of perception and action with that level of abstraction is really challenging, from a modeling point of view. From a, from the point of view of the brain, it's just what we're built to do. Okay. So this now at least lets us see not just the kind of grammar of this instruction, but actually the kind of causal mechanisms that that are called for. So what we need to do is the robot has to orchestrate a motion event resulting in the bags being upstairs, generated by a process in which the robot supports the bags so that they move with the robot. Okay, so like you might think, oh great, well we're done now. We just do this action, right? Right? And sort of, anyone who's read the story The Monkey's Paw knows that it's not going to be that simple. And here's a point where there's actually AI research that has long led the kind of cognitive science enterprise, because what's missing from the kind of bare bones account on the slide that I'm showing now is the idea of collaboration, the idea that like the instruction has to somehow be carried out kind of charitably and relevantly and usefully for the instruction giver. And we can actually make precise what that involves. So one thing that we just need to say off the bat is that the instruction is likely to omit obvious preparatory steps that would be necessary to carry out the kind of action that's being described. So if I say, I'm probably, you've given instructions like these, if you've, had to arrange to meet a friend on campus in person. I don't know if that has happened yet, really, but to get to Rutgers, take exit 9 on the turnpike. Well, that's true, but how do you get on the turnpike? Well, like that's up to you. Like, people can do that, but it's not as though like you say this does not compute. I'm not on the turnpike. You say, okay, well, I'll take the obvious preparatory steps that this person is not in a position to give me detailed instructions about, and I wouldn't want them anyway. Right. So obviously, like the robot might have to go to the bags, pick them up. There's going to be a certain amount of planning that takes place just to get into the position to make this action happen. This action is not a complete description of what's going on. It's a sketch that, among other things, omits obvious preparatory steps. that's relatively easy. This is a more funny thing. Sometimes when you give an action like this, like the result of the action is the goal of the instruction, but sort of what happens next is not clear. So if someone says, I'm going to take the kids to school, like probably they're going to leave the kids at school and come back. If someone says I have to take my dog to the park, probably not. They're not going to leave the dog there and come back. And there's nothing in the language that says that. What says that is sort of the role of the instruction in the collaboration and sort of what makes sense. So in this case, if you say carry the bag upstairs, this is not exercise. It's not like the bags need to be upstairs in order to, relieve themselves and then can be carried back downstairs. The point of the instructions is the robot is going to drop the bags at the destination and probably return afterwards. So there's an inferred goal that is associated with doing this action, which in this case is the bags being upstairs, but could be somehow related to the bags being upstairs. And so you need to achieve that goal. And you need to do what AI researchers call protecting that goal, which is to make sure that the other actions that you take afterwards don't somehow cause this goal to no longer be true. And of course, the collaboration has to resume afterwards. So there might be actions that are incumbent on you. So what this instruction is not, it's not like a computer program. It's not giving you a specification of the actions that the robot should take in any kind of complete way. What it's doing is saying, well, there's going to be an event of the type I'm telling you, and from that you can infer a goal that I would like you to achieve. And so what I'd like you to do is any preparation that's necessary to do this action, do the action, then having achieved that goal, which I haven't explicitly said, make sure it stays true, and then continue our collaboration. So it's this indirection that's really characteristic of teamwork, and is naturally integrated into the kinds of models of teamwork that really AI researchers have really pioneered. And here, Martha Pollack did sort of seminal research in this area before being sucked into academic administration. Martha Pollack is now the president of Cornell University. And another key player in this field is Barbara Gross, who is, again, plays a major administrative role as the director of the Radcliffe Institute at Harvard. Just to sort of say what the idea is, sort of collaborations are this extended activity aiming towards sort of complex goals where we kind of have agreements going along about what we need to make happen and who's going to do what roles in making that happen. And in supporting that, we commit to sort of how things are going to work. And we also recognize other people's commitments about how things are going to work. And whenever we take on sort of a new project, a new action that we'd like to take, we make sure that that is compatible with the commitments that we've made already. And so that's sort of what's happening here in sort of fleshing out these details about what you actually have to do to carry the bags upstairs. So I think, like this for me, like kind of really emphasizes like kind of just like how neat and coherent and yet heterogeneous cognitive science is, in that when you take a instruction like carry the bags upstairs and think really detailedly like what kinds of inferences are you going to have to do to follow that instruction, you find that you're combining like this abstract linguistic knowledge, this kind of physically deep perception and categorization knowledge, and then this kind of very like kind of flexible and human and commonsensical social knowledge, and it all has to kind of piece together in order to like even start to like at the end of the day, like I think it really is true that like when you tell someone to carry the bags upstairs, you're just telling them what to do and they're going to do it. But it turns out that the way that people do that is not just like by programming each other, but it's actually by this kind of dance of sort of social coordination underpinned by a very, very rich understanding of the world and a very like kind of systematic and highly structured linguistic system for kind of regiments the communication. Sort of, I think the kind of coherence and interest of cognitive science as a field comes from the kind of power of putting together these different disciplinary approaches and recognizing that the kinds of knowledge and inference that are happening at each level are kind of qualitatively different and sort of each in their own way, like kind of powerful and surprising and very, very deeply human. So I think it wouldn't be, so like that's the upbeat part. And I want to say like this pretty much works. There's some really great implementations of it. If anyone's interested, you can do surprisingly well. It's just like a class project. And then, if people want to see how computer scientists really do this nowadays, you can see the video that I put in chat. It's totally different, which, in some ways is disappointing, but, it makes my job pretty secure, I would say. So with that, why don't I take questions? And, maybe we can, this was too much of a lecture already. So I think maybe, hopefully we can have a, I'll invite anyone who wants to start the discussion, like to tell a story about, their own misinterpretations, like I took the children to school, but then I was there and I had them there, so I took them back. Like, why wouldn't I? That's what I do with the dogs at the park. All right, I'm going to stop sharing. I can obviously return to this at any point, but I will. See this matrix of
Hello.
hey.
Yeah. So I have like I recently listened to this talk by Jeff King, the philosopher of
Yeah.
language professor.
Yeah.
And he kind of goes over some like interesting like issues that English can have sometimes with understanding. And it wasn't like about, there was no like relationship to like computers understanding it. But I was thinking like one of the issues he brings up is like these general statements. So like you might say something like horses have hooves. And it kind of seems like you're talking about all horses when you say that. But then you might say something like sharks kill people. And like, well, not even close to all sharks kill people. A very, very small, like a tiny percent of sharks kill people, even though, but if you go back to the horses example, like, I mean, a very, very, very small percent of horses do not have hooves, like almost none, right? So this seems like a kind of thing that would be just really difficult for a computer to understand. And I wonder if you've ever thought, like, had that specifically, or like a similar thing that you've thought about in your work.
So it is totally different. It's totally difficult for computers to understand. And actually, this is an area where computer scientists often cheat. And so, like, I think there's a lot of kind of work on common sense knowledge in computer science, which doesn't really attend to these distinctions. And so it's susceptible to the kinds of paradoxes and flawed reasoning that this literature and philosophy points out. It might be true that like lions have manes and lions give birth to live young, but it's the rare lion that has a mane and gives birth to live young. Yeah, I mean, and so like one of the things that computer scientists can do methodologically to keep themselves honest is to try to connect language processing and kind of common sense reasoning work to some kind of real world task, like robot manipulation or where in some sense, if any of the knowledge that you acquire from language is false, the system is going to do something bad.
Is it right if I ask a follow up to that? Or
go ahead.
Yeah. So, kind of like on this like issue of interpretation. It's not, you see, like when you're giving a robot a command, I would imagine like you have to, the robot has to figure out like the sequence that you want it to do something, and like a way that humans sometimes describe sequence is using and statements, which is but then not always. Sometimes we should use and statements, and we don't mean do this in the order I'm saying my and statement. I just mean do these two things. And I have you come up with it? Like have you run into that problem before?
Well, right. So what I would say is that kind of my approach to sort of those kinds of ambiguities is based on a common idea in computer science that I guess is kind of the two people that are most associated with it are Alex Laskaridis at the University of Edinburgh and Jerry Hobbs at the University of Southern California. And this is the idea of discourse coherence. And the idea of discourse coherence is that essentially, in order to understand how two sentences fit together that are sort of joined together with and or other kind of underspecified connectives, is that you're fitting them into some kind of high level schemas that you can use to disambiguate it. So you might be like in the kind of flow of time, that's a kind of narrative relation. There's also a kind of parallelism relation where you're just pointing out that these things are somehow related or different in some ways, and that tends not to have any temporal implications. And then there's a kind of cause-effect relation where you understand a more specific relationship than just temporal succession because of some explanation that the speaker is providing. And so there are lots of cues that you can use to do those disambiguations. And some of them are sort of surfacey, like parallel structure, and those tend to work well. And some of them, like the causal relationships, tend to be very, very hard for current NLP techniques to find. So, so you can get a lot of them right, but right now you get so many of them wrong that it's hard to build systems based on that information that have to be reliable. Yeah.
Thank you.
So Cynthia, do you want to come on and ask your question? I'm happy to answer it directly if your microphone's not working or whatever.
Hi.
Hey.
Yeah, I just want to, I guess you, in the beginning, you said that there are like a lot of like people at Rutgers doing this kind of like work or research, and I was wondering like what kind of, I guess, opportunities or like what kind of stuff is going on at Rutgers, more specifically like pertaining to, I guess, natural language processing. And I'm like interested in it. So I was wondering, like, I'm also building my schedule for next semester and stuff right now. So I was wondering, like, do you think computer science or linguistics is more important? Because right now I'm thinking about doing like a cognitive science, computer science double major, but I'm also taking like intro to linguistic theory right now. It's like pretty cool. And I'm not really like, I don't want to get like too technical with like computer science stuff. So I was wondering, like if there's like more of, I guess, like a linguistics approach, like how would you like, I guess, take a more, I guess, linguistics approach to maybe this type of subject? Or do you think it's like really important to also like have like computer science, like fundamental stuff like down, I guess?
So there's actually, I would say, 3 or 4 different ways of doing natural language processing. And I want to, for like the whole audience, get them all out on the table because I think the answer might surprise you. So in terms of like actually using NLP tools and sort of using NLP technology to answer sort of interesting questions, there's research happening all over the university because, let's say, text analytics is a really valuable tool in political science, in sociology, in planning and public policy, in information science. And so like if you like look at like what courses are covering like some text processing content in the spring, like you might find a political science course taught by Tom Davidson. No, Tom Davidson's in sociology, taught by Katie McCabe in political science, looking at how you can mine online opinion posts for evidence about partisanship, or people like Britt Paris or Vivek Singh or Jeffrey Lane in the School of Communication and Information are looking at, again, mining these text collections of online interactions or other kinds of, or news articles or other things like this to get a read on how people are, like just what the problems are in society, what the what the networks are in society, what the impact is of technology and online interaction. And this is like some of the easiest ways to kind of get involved in NLP work at Rutgers. And what it actually requires, rather than computer science or linguistics, is actually kind of data science skills, meaning like sort of being able to import text data into a statistical environment and being able to run hypothesis tests and visualize the data and understand the impact of missing data or understand the possible biases in the data set, things like this. So, you know, don't rule that out. That's, there are a lot of opportunities at Rutgers like that. Within computer science, there's kind of two tracks. There's work that the kind of work that I was talking about, that's about building like kind of interactive systems that use language. And that's often connected to robotics. So Kostas Bekras has students that are working on robot instruction following. It's also related to computer graphics and interaction. So Mubasir Kapadia has students that are working on chatbots and sort of social avatars. And so that is a less technical part of computer science, because a lot of it, like in my work, involves like running experiments with human subjects, or, you know, like just figuring out what's better or figuring what people like. It also involves like kind of programming that doesn't have to be super complicated, because like if you want to like use a computer graphics package to animate a face or something like that, it's more like scripting than like you know, hardcore algorithms. But then there are people that are doing like real like kind of machine learning experiments where it's like understanding how can computers draw inferences about language. And Carl Stratus and Sun-Chin Ahn are the people that do that kind of work. Carl's giving a talk on Tuesday morning in the computer science department. But I mean, that on the linguistic side, it's I'm not sure how. I would say like Maria Paula D'Imperio does this more data sciencey work, and she's probably the professor that's kind of most connected to you know, to the kind of practical programming for doing linguistic analyses. But then there's a lot of research that like with Bruce Tesser or Kristen Surrett, where people are building computer models that like kind of illustrate theoretical ideas and help to differentiate between like kind of different linguistic theory proposals. And so that's not really, that's like computational methods, but it's not really natural language processing. It's really linguistics in a way. You know, so that's kind of the landscape. A lot of, you know, like the work that I do, like I really prefer to have a mix, like an interdisciplinary team with some, you know, a linguist or a philosopher, a psychologist or another social scientist, and a computer scientist or statistician, you know, sort of all handling different aspects of the project, because, you know, like for the reasons that should be clear from my talk today, like, you know, like it's going to be one thing to write the grammar, it's going to be another thing to do the inferences, it's going to be another thing to relate to the people. And unless you have all of that in the system, it won't work. Thanks. Is that good? Do you have any questions to follow up?
Yeah, thank you.
If you don't mind, I have some questions, but we are at the end of our meeting. So if you guys you know, if you have somewhere to be, thank you so much for coming. We appreciate it. If you want to stick around, and Dr. Stone, you're okay with us sticking around for a bit? Okay, cool. So if you want to stick around and ask some more questions, then feel free. Kenny, were you about to unmute?
No, I'm good. Thanks.
Okay, sorry. I thought. Okay, I imagined that then. So, I had a question mainly about I was gonna say like compound sentences, and then having the robot or whatever machine that you have adjust for when you add a new action, right? So for example, climbing up the stairs versus carrying something and climbing up the stairs are two completely different things, because you're putting different kinds of weights, and you have to adjust, your center of gravity is different. You have to now adjust, you know, the balance, and then carrying and the center of balance and the kinds of calculations that that robot has to make then depends on how high the stairs are, how many steps there are, right? So it's like, it's like, it almost seems like an impossible task to, because there's so many different nuances. And we were just talking about simple sentences and simple commands, but then when you add different elements and you add multiple commands and layer them onto each other, I feel like, I mean, what are your thoughts on that? I mean, I can't see it being something that's practical for, but I mean, what do you think? I don't know.
No, it's not going to be. I mean, it's a long way away. You know, that's why I work at a university, and, you know, not at Boston Dynamics or whatever. So one thing to just kind of bear in mind about, like, so when you say to a computer scientist that the solution is going to involve solving a planning problem, like, that gives you access to a long history of very kind of powerful ways of using computers, right? So, you know, like, you know, when people approach like a game like chess or Go, they, you know, like, there's a lot of nuance
there's more
and
brute
complexity
force
to it.
with
But
with computers.
there's, you know, it's possible to build a computer system that has really impressive capabilities in there. And like, and it's also true that, like, if, you know, I think the way to think about you know, sort of like action in the world is similarly, like, if you look at like some of the things that the Boston Dynamics robots can do, they're like freaky, scary.
Yeah.
And what makes it successful to do that is that there is this kind of problem solving under the hood, that there's this really efficient, but really at the same time compute intensive way of exploring all of the possible actions that are available to the system in a way that sort of simulates the ones that would lead to good outcomes, taking into account all of the subtleties of the circumstances and the loads on the system and the you know, so you know, so I have a lot of optimism that kind of problem solving as a programming technique is going to be able to you know, lead to, you know, sort of appropriate actions and context in a kind of proficient way, provided that we can have like kind of good perception and good simulators and a good statement of what goals the system should be achieving. And those are, you know, sort of, that's not an engineering problem as much as it is a scientific problem, because we actually don't know that much about how the common sense world works. We don't know that much about the kind of common sense relationships that people have with one another that they, you know, sort of use to get things done together.
Yeah.
Yeah.
Then do you think that you run into the problem, and I'm not a computer scientist or someone that codes often, but I have friends that do, you know, other eBoard members for this club do, and we've had people guest speakers come in and we've talked about this before, but do you think with something as complicated as that, and as you said, having the opportunity to use very powerful computing to brute force your way through these kind of problems, do you think you run into the problem of like having almost like a black box where you don't understand what the code is actually doing? It's just there's so many,
Yeah, definitely. Yeah.
right?
Yeah,
So
yeah,
how do you
yeah.
would it be better to then go down that road rather than finding models that are more easily explainable, and models that, I don't know, make more sense in terms of what they're doing? As you said, it's not just about like, in terms of them not just being focused on achieving a goal, but mimicking the process that achieves the goal, so to speak. And yeah, if that makes sense. So my question is like, what's better? Do you think it's better to attain the goal first and start approaching these problems that way, and then kind of hit a roadblock where we don't know where to go next because we don't know what we just made, or make it easier to understand, make it more interpretable, make the code, make the process more interpretable?
So, I mean, I think the thing to just bear in mind that like the people that are interested in the science would only want explainable models, because it's sort of like, you know, if what you want is an explanation, then a black box isn't the answer to your question. A lot of the, you know, sort of debate around black boxes versus explanations is actually focused on like what's the right choice for kind of practical problems in industry, like for particular applications. And there, in some sense, the real question that you're asking is not like, it's not about like, should I have an explanation or should I have a black box? It's really, how do I make trade-offs between average case performance and worst case performance? Because basically a black box will win on average case performance. But, you know, sort of as we've discovered, there's sort of inherently no guarantees about worst case performance. So, you know, so they can be very unfair. They can be very dangerous in some cases. And so like the question around explainability is like, where are the problems as a society where we think the worst case outcome is what we need to be engineering for? And you know, we already have that kind of safeguards in place with airplanes. We don't build airplanes with a technology with the best performance. We build airplanes that won't crash. And that kind of explainability is sort of a design choice we've made as a society about the reliability that we want these devices to have. And so like, you know, with airplanes, we're willing to wait 10 years for the next generation of planes because we as a society value safety. And, you know, like, you know, whatever, we're waiting for the day where we feel the same way about social media.
Sorry. So you're saying like an explainable model is somewhat of an ideal, and having a more attainable solution, it's really like more, it's a balance based on what your needs are for that particular project or product or whatever it is. You use the example of
Yeah, it's not unattainable.
right.
It's just slow and expensive.
Right. Okay. Okay. Thank
I'm
you.
sorry, I have to go. All of my children are looking at me for things. So, but thank you so much for the interesting talk.
Thanks, Kenny.
Wait. Do Do you want to say something, Ion?
No, I was gonna say, does anyone have any more questions?
Oh, I was just wondering, like, how much, like, I guess progress has been made towards a more like explainable model of language for computers. Like, I'm not really sure how computers like process language right now, but like, I feel like the best way to understand language would be to like, I guess like assign, yeah, like every word like roles like they're part of speech, or like all of like the tree drawing stuff I'm like starting in linguistics right now. But like, I guess, is there any like, do people like work towards modeling that in computers, or like has I guess like how developed is like, I guess, a theory of computer understanding in like that way, rather than just like brute force figuring it out?
So there's a lot of really good work like that. You know, I like pointing people to the Universal Dependencies Project. One of the leads on it is a linguist called Mary Catherine Demarneff at Ohio State. It's very closely, it's very closely related to one approach to formal grammar. It tends to gloss over some distinctions that linguists think are probably really important. But it also, for computers, it's, what's cool about it is that it actually uses representations that kind of build in some key assumptions of universal grammar. Assumptions that we don't know how to capture in any other way. So when you build a parser with in this framework, it actually kind of inherently captures a lot of generalizations that seem to be universal in language. And a lot of the machine learning techniques that people have developed in these brute force systems are also applicable in these sort of dependency frameworks. But instead of just sort of giving you an inexplicable answer, yes or no, these systems will give you a tree and like tell you what they kind of reconstructed for the structure of the sentence. And, you know, it's really fun because there's a lot of code to play with, but there's also a lot of data sets for, you know, like 50 languages or something like that, so that you can see how the theory applies in a lot of examples, and even, you know, sort of train your own parsers using these general frameworks to adapt to these different languages. So yeah, so there's definitely close relationships in NLP. It tends not to be the most, you know, it's scientific in the sense that like, it's still very hard to make a system that does anything better because it has a parser, as opposed to like just more shallower statistical models that don't assign structure to sentences explicitly. But there are a lot of applications essentially where they won't work unless you assign the sentences a tree-like structure. And for those things, you need to have a technique like this. And so people keep working on them also because of their scientific interest.
Luna, do you have any questions?
No, I'm good.
Okay. Are we good, dude? Cynthia, do you have any more questions? I'm good. Yeah, I'm good.
Yeah, thanks for your interest. It was very fun. Like, I hope the talk wasn't too hard. You know, sort of it's sort of like one of the things that I always think is crazy about cognitive science is how complex you can make this very simple thing. Sort of a blur, but yeah, you have to kind of have the patience to work through it. But it makes sense in the end.
Yeah, with enough, definitely. Yeah. Okay. Well, thank you so much for coming by. I really appreciate it.
Yeah.
It was a great talk.
Yeah, thanks.
Had a lot of fun. Bye.
I feel like I was gonna say something, but I can't remember now. Not to him, but just like at the end of that when we were here. I don't remember now.
Wait, did we take the pic? Did anyone take the pictures? From
I took
library?
pictures.
Okay, good. Because I was like, oh, that's a thing. Then I forgot.
I took a couple. Yes.
Okay, cool. See y'all.
Okay.
Yeah.
Bye.
Bye.
I'm trying to think. Now I can't remember. I'll just text you. If I
Thank you for starting the room. I completely slipped out of my mind today.
Yeah,
I
it's
appreciate
no
it.
worries.
Thank you.
Yeah, Mariam like texted me being like, "Oh, is the room open yet?" And I was like, "Oh, I should probably do that then." And
Yeah.
then I didn't realize. I don't think he had the Zoom link, so to email him last
He
minute.
didn't. No, he didn't.
Okay, so
Yeah,
I
we
was
gotta
like, "Try to do that."
gotta do that in advance. Like when we do
Yeah.
the weekend checkup, I think we should send, or the week before checkup, we should.
Yeah, I'll probably email
send the
Dr.
Zooms.
Misro
For
his.
Dr. Yeah.
I'll email him when he gets back to me.
And that's fine. You don't need to do it today or anything. It doesn't have to be exactly a week. Just like around the same time frame that they send out the emails and
Oh, I already sent him the email today. Like,
Oh, good. Awesome.
Yeah.
Okay.
so I'm gonna see when he responds. So yeah, I think we're good.
You can stop the recording now.
Oh yeah.